Hello, physics students. Let's go ahead and talk about specific heat very briefly. Specific heat is all about one simple equation, Q equals mc delta T, where Q is the heat in whatever object or substance, m is the mass of that object or substance, C is the specific heat capacity. Remember, that's a measurement of how much the material resists changes in temperature, and there is the change in temperature of the object. Now, when we're dealing with specific heat in equations and in experiments, there are always going to be two sides of things. We're going to have negative Q equals Q. And all we're doing is we're putting that negative sign in there because remember that one object or substance is going to be cooling and the other is going to be heating up. And heat is a little bit like a vector in that it does matter whether the energy is coming in or out, and that's why we have to have the negative sign there. And you'll see how that plays out as we get deeper into the example. This is our basic relationship. When you do this in an experiment or a sample problem, remember that you need to take into account both the object and its environment. We're going to be talking about a piece of metal here, which will be cooling, and the environment it's going to be in, we're going to drop it into a container of water. So over here for the metal, I'm just going to make up numbers, literally. So we're going to say that the mass of the metal is, let's say we have 20 grams of it. Again, making numbers up off the top of my head, let's say the specific heat capacity is 0.2, and it changes temperatures not by 15 degrees, but negative 15 degrees, again indicating that the metal is cooling. Over here, the container of water that it's going to go into, let's suppose it has a mass of 50 grams. We do know the specific heat of water is 4.184, and I'm leaving units off just for brevity. And suppose we want to know how much that water is going to change in temperature as a result of this hot piece of metal being dropped into it. All we really have here is a simple plug and chug equation. We have the object which is cooling, which is the metal. We have the object or environment which is heating, which is the water. And we're just combining these two equations. So we're going to have mc delta T for the metal over here on the left, mc delta T for the water over here on the right. Yes, those of you who are looking at the details, you know that I should be putting this subscript on each of these three items on the left and each of the three on the right, but just trying to move fast and keep it a little less cluttered. All we do now is we do a little bit of plug and chug. We're substituting in, so we know that the mass of the metal was 20.0. The specific heat was 0.2, and the change in temperature was negative 15. On the other side, that's going to equal, plugging in over here, 50 grams of water. Oops, I don't need to put the G in there. Physics and chemistry students who aren't in my class, who stumble across this online, yes, some of your instructors will require you to put the units in for each measurement. I don't. So 4.184 is the specific heat capacity of water, and we don't know what the change in temperature is yet. That's our unknown. That's what we're going to be trying to solve for. At this point, it's just calculator work. Plugging all of these into the calculator, 20 times 0.2 times negative 15. Whoops, I forgot my negative sign out here. This is going to be 6.0, because again, we've got a negative and a negative that's going to turn into a positive. Over here on the right-hand side, 50 times 4.184 is 209.2 times delta T, because that's still our unknown. To find out how much the water changes in temperature, we simply need to solve for this part of the equation, which means we want it to be absolutely alone on that side of the equal sign. We're going to undo this multiplication with division on both sides. Golden rule of algebra, do unto one side as you would do unto the other. And in the end, the change of temperature is going to be 0.03 degrees Celsius. Yeah, throw that in there. Now, important things to notice. Yes, it makes sense that the water would only change temperature by a small amount. One, because there's a lot more water, and two, look how much higher that specific heat capacity is compared to this made-up number for this made-up metal over here. It is important to note that we have a positive value over here. You can't have both the metal and the water cooling as a result. One of them has to get warmer. So we know that the metal is cooling down, the water's got to warm up, so that's a positive, so water will warm up ever so slightly. And that just goes to show again that this negative sign up here is important for showing the direction. That's your simple example worked out. I hope this was helpful to you. Let me know if you have any questions about this as you work through the lab.